Another technique of integration is what's known as trigonometric substitution, and it's useful when we have quadratic type of equations, things like a squared minus x squared, square root of a squared plus x squared, or x squared minus a squared, the square root of that. What we'll do is we'll take advantage of some of the Pythagorean trig identities, and we'll make certain substitutions to take advantage of them. The general rule is that if you see the square root of a squared minus x squared, you can replace x by a times the sine of u. If you see the sum, you can replace x by a times the tangent of u, and the difference, x squared minus a squared, a times the secant of u. And what we're doing is we're taking advantage of some of these trig identities, similar to sine squared x plus cosine squared x equals 1. And the two cousins, the actual, just the one cousin, tangent squared plus 1 equals secant squared. That would be useful in these last two. Our example that we're going to use to do this is the integral of x cubed over the square root of x squared plus 4. So as we saw in the previous slide, we want to choose x to be equal to 2 times the tangent of u. Then we need to find out what dx is, and this is kind of nice because all we have to do is take the derivative of this to get dx. Derivative of tangent of u is secant squared of u, so we'll end up with 2 secant squared of u du. We'll make these substitutions. X cubed becomes 2 tangent of u cubed. X squared becomes 2 tangent of u squared. And 2 secant squared u du is what used to be dx. Now with a little bit of simplification, notice that we're going to have a 2 cubed, another 2, so we're up to 16, but then we can factor out a 4 from the square root because that 2 squared is going to give us 4. If we factor out 4 and take the square root of that, we'll end up with a 2 in the denominator, which would essentially eliminate that 2. So we're going to end up with 2 cubed overall. So a small simplification, and this is where we end up. Alright, we'll start over here on the 9. Okay, same integral. Now, we're going to take advantage of the fact that 1 plus, that should say 1 plus there, the tangent squared of u is equal to the secant squared of u. So this is the square root of the secant squared, which just becomes the secant, which will reduce and we'll lose the power there. Okay, so now we've reduced it down to tangent cubed of u times secant of u. And now I need to remember my two derivative formulas. Derivative of the tangent is the secant squared, and the derivative of, these should be with respect to u, I apologize for that, derivative of the secant of u is secant of u tangent of u. Okay? We're going to try to use one of these to our advantage in evaluating this integral. If I wanted to try to use the first, I would need to have a secant squared. That's not going to happen because I only have the secant, so that guy is out. This is the one we want to try to use. In order to do that, we're going to need to pull off one factor of the tangent of u. We'll see what happens. I pull off one factor of the tangent of u, that leaves me with tangent squared of u. But remember, this is the derivative of the secant of u. So I have to write the tangent squared of u in terms of the secant of u, and if you solve that one equation we had up just a few moments ago, tangent squared of u is simply going to be equal to the secant squared of u minus 1. So I'll replace that, and now I can make a substitution. U will be equal to the secant of u, or w will be equal to the secant. There we have it. So now we can Replace this with dw, and secant of u is going to become w squared. This is a straightforward polynomial integral. So the integral of w squared, 1/3 w cubed, we subtract w, and we don't want to forget our little constant there. And now, here comes the fun part, substituting back all the way back to x. Well, remember that w was equal to the secant of u. So we get 1/3 of the secant cubed of u minus the secant of u. But we need to remember now that x was 2 times the tangent of u. Now if I solve this for the tangent, we get the tangent of u is x over 2. And so what I want to do is I want to imagine u as the side of a triangle. Or the angle in a triangle. So there's our right angle. Here is u. Tangent is the opposite side, which is going to be x over 2, the adjacent side. If you do a little maneuver with your Pythagorean theorem, you'll find out that this is x squared plus 1. Plus 4, that is, I'm sorry. Okay, a little hard to read there. But that says square root of x squared plus 4. And so the secant of u, well, I remember the secant is the reciprocal of the cosine. Cosine is adjacent over the hypotenuse. So the secant will be the hypotenuse over the adjacent. So every secant squared, or secant that I have, will become the square root of x squared plus 4 over 2. So the secant was cubed here. We take the square root of x squared plus 4 over 2. We cube that. Secant of u is the square root of x squared plus 4 over 2. And now it's just a matter of simplifying. We're going to have 2 cubed, which is 8, but that's in the denominator. So when I distribute this 8 through, it's going to cancel with that one. When I multiply 8 by the 1/2 that's over here, we're going to end up with 4. And there's a final prettified answer.